In this video, we're going to take a look at calculating bird species range using data from BirdBuddy. BirdBuddy is a smart bird feeder that captures bird observations and identifies the species using computer vision. And then they make that data publicly available, which we can download from the BirdBuddy website. We're going to load this data into Sedona DB using Wherobots Cloud and calculate the range of each species and then visualize the results. So we'll be using Wherobots Cloud. If you'd like to follow along, go ahead and create a free Wherobots Cloud account and go ahead and get signed in. So I'm already signed in to Wherobots Cloud and I've created a new blank notebook. So let's go ahead and first get started with some configuration and importing our dependencies. So I'm going to import the Sedona Spark package. We'll also import GeoPandas and the requests Python library. By default, many Geospatial and PyData packages are installed in Wherobots Cloud, but we can always install packages we don't need just using pip. And we'll do some basic configuration. We'll leave this mostly blank. You may see other examples that specify credentials for AWS buckets or different file access here. We don't need that for this example. And we'll pass through our config object. And once we've done that, we'll need to fetch our data. So our data is coming from BirdBuddy, as I said, which we can download here. I went ahead and downloaded 1 month of data and uploaded that into my Wherobots Cloud file management system. Now, a free feature of Wherobots Cloud is file management using S3. So you can see here I've uploaded some files. To do that, we just click this upload button and select, in this case, the CSV of BirdBuddy data that I downloaded. You can see some other files here that I've uploaded, and then we'll just copy the S3 path. Now, that S3 path, that's private to my Wherobots organization, so others won't be able to see that. Let's go ahead and import this data. So the first thing we'll do is create a variable for our S3 URL. And again, this is private to my Wherobots account. You'll need to upload data to your own account. You won't be able to use this URL if you're following along. And then we'll create a new data frame by reading this in using the Sedona reader, reading as CSV. There is a header, and the default delimiter is a comma, and we'll load that from our S3 URL. And then we'll just go ahead and list the first few rows to see what kind of data we have. So we can see we have a latitude column, a longitude column, timestamp, and then 2 different columns to represent the species, the common name, and the scientific name. So let's convert this to use actual geometry types and query this data using Spatial SQL to see how we can compute the range of each species. So I'm going to use the select expression builder, which just helps us to build a select SQL expression, specifying what columns we want to bring through. So we're going to use the stPoint function. This is a Spatial SQL function for creating point geometries. Now, in our CSV that we imported here, by default, all of these values come through as string values. So we're going to need to cast our anonymized longitude as a numeric value. We'll also cast our anonymized latitude point. And by anonymized, I think they just mean they adjust the location of the bird feeder a little bit, so we're not giving out the exact location of where folks have their bird feeders. Okay, so this will create a point geometry column. We'll call that location. And then we'll also bring through the timestamp, the common name column, and also the scientific name column as well. And then we're going to create a view, and we'll call that BB. By creating that view from this data frame, that will allow us to query this as a table using Spatial SQL. Cool. So now we have actual point geometries representing the location of where we observed our different bird species. We can do things like get a count on the data frame, compute the number of rows, so how many observations do we have of these different species. And again, I downloaded just 1 month of data. I think there's a year or so of data to work with, so we could combine or import multiple CSV files, but I think this is a good way to get us started now. So we have just almost 14 million observations. Well, let's take a look at some of this data. First, let's query to just find juncos. So juncos, that's a pretty common group of species. So let's filter for where the common name contains junco. And we can show the first few results. So now we have just some junco observations. Let's visualize those using Sedona Kepler. So Sedona Kepler, this is a integration with Sedona and Kepler GL, which is a visualization tool for creating interactive visualizations in our notebook environment. So Kepler is very useful. We can visualize different geometry types, and then we can configure the visualization with different types of styling, depending on the type of visualization that we're creating. Here, we're just going to visualize some point geometry, so the distribution of juncos throughout North America. And so we can zoom out, we can zoom in, so we can see that the junco has a pretty wide distribution range. What's nice about Kepler is we can do things like filter the results. In this case, because we have a timestamp value, we can filter by time. We can also play these over time to see how the distribution of junco observation changes throughout time. So that's pretty neat. Okay, so we said the goal for what we wanted to do today was to take these point observations and calculate the range of different bird species. So to do that, we're going to write a Spatial SQL statement to convert the point observations to polygon observations using the convex hull function. And then we'll do this in a group by, so that we'll be able to group those geometries by bird species. So let's write our Spatial SQL statement to do exactly that. So we'll start off using a common name. we'll just do a count star of the rows, so the number of observations. And then to convert the point geometries to a polygon, we're going to use the st convex hull function. So this is going to draw a convex hull, which is basically a polygon that will contain all of the point geometries that we're going to pass to this function. We need to aggregate those together. So we're going to do an st union aggregation using the location, so the point geometry, and we'll call this the geometry column. This is coming from our BB view. And let's do this for just a handful of bird species. So these are some of my favorite birds. So the California towhee, the Steller's jay, and this is in the data set, this is a smart quote. So on Mac, that's Option Shift bracket to get the sort of smart quote. For Steller's jay, the mountain chickadee, and how about the eastern bluebird? And we want to do a group by the common name so that our convex hull and this aggregation function here, those values are grouped by common name. So we'll end up with one convex hull for each of these species based on all of the point observations for those species. And then let's order by the number of observations in descending order, just so we can get an idea of what are some of the most common bird species that we're seeing. So this operation will run, and what we'll end up with is a new data frame, range df, that the geometry will no longer be point geometry. Instead, the geometry column will be polygons representing the convex hull, or the range of each species based on the point observations that we found in the data. And we can also see the most common observations, by species. So we have almost 66,000 observations of the eastern bluebird, 38,000 of the Steller's jay, and so on. Looks like our mountain chickadee seems to be one of the least observed, at least in the species that we're filtering for. So now we can visualize this all again using the Sedona Kepler integration. And so to do that, we pass through our range data frame, give that a title, and now we can visualize the range polygons of each of these species, and we can style those results however we like to visualize within our notebook environment using Sedona Kepler. We can do things like create a unique color for each geometry and things like this. So here are the ranges, the range polygons of each species. And if we go into the configuration here, we can set the fill color to be determined on one of the fields, in this case, common name. Maybe we can choose not a color ramp, but something that has maybe something like that to identify the colors. So this is good for visualizing the data within our notebook environment. But what if we wanted to share this visualization with others? Well, one way we could do that is to use a web mapping tool like Felt. Felt is a web-based tool for creating interactive and collaborative maps. Felt has a API, so we can share this data programmatically to create a new map and layer in Felt. So let's go ahead and do that, the Felt API takes data in lots of different formats. One of those is GeoJSON. So let's convert our range data frame to GeoJSON. There are a few ways to do that. We'll do that today by first creating a geodata frame. And to do that, we'll take advantage of the toPandas method on our data frame, which will convert our range data frame, which is a spatial data frame, into a pandas data frame. Then to convert to a GeoPandas geodata frame, we need to specify the geometry column. And then we'll save this to a file. Let's call this birdbuddy range.geojson and specify that the driver we want to use is GeoJSON. So now we have created a GeoJSON file, and this is saved in our Jupyter environment. And now what we want to do is use the Felt API to upload this data to a new Felt map and do that programmatically. So the first thing we'll need is a Felt token. So you can create a Felt account for free, and then in the integration settings, just create a token. And don't worry, I'm going to deactivate this token before you see this video. So if you're following along, you'll want to create your own Felt token. And then just so you don't have to watch me type this in, I wrote a Python function to use the Felt API to upload a GeoJSON dataset and create a new map. So I'm just going to copy that in, and I'm going to paste that in just so you don't have to watch me type that, but we'll go through this function to see what we're doing. So this function is called create Felt map. It takes an access token, the GeoJSON file name, the title for the map we want to create, and then the name of the layer that we're going to create. And so this is actually making several calls to the Felt API. First, we make a call to create a new map to the maps endpoint, specifying the name of the map we want to create. And then we create a new layer, and this layer will return a pre-signed URL that we can use to upload data. We can upload multiple files. In this case, we upload just one. And then finally, we call the finish upload endpoint to indicate that we are done uploading data to this layer. So now that we've defined that function, let's go ahead and call it. So we'll pass in our Felt token, the name of the GeoJSON file that we just created, the name of the map, and the name of the layer. We'll go ahead and run that. And we can see some information that's logged to the console here. So we get the URL for the map. We have the pre-signed URL where we can upload data, but that's already been done. So let's go ahead and take a look at our map in Felt. So we said that Felt is a web-based tool for creating and sharing interactive maps. So here are our polygons. Let's style these a bit using categories to style those. So now we can see the individual ranges of each bird. Here's the range of the eastern bluebird, the Seller's jay, mountain chickadee, and we can see our other species behind the others. That's going to be our California towhee. And we can tweak the styling a bit. Maybe if we make the opacity a bit different, there we go. We can see better the range of our California towhee here. Cool. So we can take this URL and share it with others. We can also embed this map in our notebook environment or in a web page. But this is the results of our geospatial analysis, turning smart bird feeder point observations into the polygon range of bird species throughout North America. So we saw how to get started with Wherobots Cloud. We saw how to take advantage of the file management based on S3 in Wherobots. And we saw some examples for using Spatial SQL and some visualization opportunities to analyze geospatial data in Wherobots Cloud. Let us know if you found this tutorial useful. If you'd like to see different types of tutorials going forward, let us know what you'd like to see. I'll be sure to add the location for the code in the video description and also where we found the data. Well, that's all for now. Thanks for watching. Cheers.